Welcome to a journey beneath your feet, where the ground itself tells stories of patience, movement, and endless transformation. Tonight, we're going to explore the gentle dance of our planet's surface, the slow and steady shifts that have been happening since long before any of us were born, and will continue long after we're gone. Let yourself sink into comfort as we discover how the very earth beneath us floats, drifts, and dreams in geological time. Imagine lying on a warm beach, feeling the sand beneath you. That sand, those grains, they've traveled so far to reach you. Some of them might have started their journey in mountains that no longer exist, worn down grain by grain over millions of years. The beach you're resting on is temporary, just like everything else on Earth's surface. But there's something deeply calming about that impermanence, knowing that change happens so slowly, so gently, that we never have to worry about it in our brief, beautiful lives. The ground beneath you right now is moving. Yes, really moving. But don't worry, you can't feel it. It moves about as fast as your fingernails grow, just a few centimeters each year. Think about that for a moment. In the time it takes you to trim your nails once, the massive plate of rock beneath an entire continent has shifted that same tiny distance. There's something wonderfully peaceful about that pace, isn't there? No rush, no hurry, just steady, patient movement. Our planet's outer shell is broken into these massive pieces we call tectonic plates. Picture a cracked eggshell, but the egg inside is still warm, still alive with heat from Earth's formation over 4.5 billion years ago. These plates float on a layer of hot, flowing rock called the mantle. The mantle moves in slow, circular currents, like honey warming in a pot, and these currents gently push and pull the plates above. There are 7 or 8 major plates, depending on how you count them, and many smaller ones. The Pacific Plate is the largest, covering much of the Pacific Ocean floor. It's about the size of all the continents put together. Right now, as you listen to these words, it's gliding northwest, carrying Hawaii with it, moving the islands slowly toward Alaska. But this journey will take tens of millions of years, so there's no need to pack yet. The North American Plate carries the United States, Canada, and parts of the Atlantic Ocean floor. The Eurasian Plate holds Europe and most of Asia. The African Plate supports Africa and stretches into the surrounding oceans. These enormous pieces of Earth's crust fit together like a planetary puzzle, their edges touching, sliding, spreading, and occasionally colliding in the slowest of slow-motion encounters, where 2 plates meet. Interesting things happen, but even these dramatic events unfold with geological patience. Along the mid-Atlantic ridge, 2 plates are slowly pulling apart. Imagine a seam unzipping so gradually that you'd never notice it in a human lifetime. As these plates separate, hot rock from deep below rises up to fill the gap. When this molten rock meets the cold ocean water, it cools and solidifies, creating new ocean floor. This has been happening for millions of years, and it will continue for millions more. Iceland sits right on top of this spreading ridge, one of the few places where you can actually walk on the boundary between two plates. The island is literally being pulled apart, growing wider by a few centimeters every year. Hot springs and geysers, the landscape, gentle reminders of the warmth still rising from below. Visitors can stand with 1 foot on the North American plate and 1 foot on the Eurasian plate, straddling two continents, though, of course, it feels like solid, ordinary ground. The spreading happens so smoothly, so steadily. New rock forms at the ridge, and older rock slowly migrates away, pushed aside by the newer material. It's like a very slow conveyor belt, or perhaps like tree rings forming in reverse, with the newest layer always at the center. The oldest parts of the ocean floor are about 200 million years old, found far from the ridges, near the edges of ocean basins. That might sound ancient, but it's actually young compared to continental rocks, some of which are over 4 billion years old. Let's drift across the Atlantic now, riding that slow current of rock. It would take millions of years to make this journey, but in our imagination, we can do it in moments. As we approach the edge of the ocean basin, the seafloor begins to dive beneath a continental plate. This process, called subduction, happens in the deepest parts of the ocean, in trenches so far down that sunlight never reaches them. The Mariana Trench is the deepest point in Earth's oceans, formed where the Pacific Plate dives beneath the smaller Philippine Plate. It's nearly 7 miles deep, deeper than Mount Everest is tall. Down there, in that profound darkness, the seafloor is slowly, steadily descending back into Earth's interior. The rock that formed at a spreading ridge millions of years ago completes its journey here, warming as it goes deeper, eventually melting and mixing back into the mantle. It's a cycle, a circulation, like breathing but on a time scale that makes mountains seem temporary. This recycling of ocean floor keeps Earth's surface fresh. In geological terms, unlike the ancient continental rocks that have been around for billions of years, ocean floor is constantly renewed. Every piece of seafloor alive today will eventually return to the mantle, and new seafloor will take its place. It's oddly comforting, this cycle of renewal, knowing that even rock, even the seemingly eternal substance of Earth itself, participates in cycles of birth and return. When an oceanic plate subducts beneath a continental plate, it doesn't go quietly into that good night, though it does go slowly. The friction between the plate, the bending and breaking of rock, releases energy gradually. Sometimes water trapped in the subducting plate gets squeezed out, and this water rises into the overlying mantle, lowering the melting point of the rock there. Magma forms, and because it's lighter than the surrounding rock, it slowly rises. Over thousands of years, it may reach the surface, forming volcanoes. The Cascade Range in the Pacific Northwest, with its majestic peaks like Mount Rainier and Mount Hood, formed this way. These mountains are volcanoes, built layer by layer over hundreds of thousands of years as magma from subducting ocean floor rose and erupted. Between eruptions, decades or centuries might pass. The mountains stand quiet, covered in snow and forest, seeming permanent and peaceful. In human terms, they are permanent. In geological terms, they're still growing, still changing, just very, very slowly. There's something deeply relaxing about volcanic mountains when you understand their timescale. Yes, they can erupt, but between eruptions, they're just beautiful mountains. Most volcanic peaks are dormant, sleeping, and have been sleeping for longer than human civilization has existed. They might wake up again someday, but that someday is likely far in the future, and when they do wake, it will probably be after plenty of warning signs. Plenty of time for everyone to appreciate the spectacle from a safe distance. Let's think about continental collisions now. When two continental plates meet, neither wants to subduct. Continental rock is lighter than oceanic rock, too buoyant to sink easily into the mantle. So instead of one plate diving beneath the other, they crumple together like two slow-motion waves colliding and pushing upward. This is how mountain ranges form, not quickly in a catastrophic crash, but gradually, centimeter by centimeter, over millions of years. The Himalayas, home to Mount Everest and the world's highest peaks, formed when the Indian plate collided with the Eurasian plate. This collision began about 50 million years ago and continues today. India, which was once an island continent far to the south, drifted northward at the blistering speed of several centimeters per year. Over millions of years, it traveled thousands of kilometers, eventually bumping into Asia. The collision was so gentle, spread over so much time, that if you could have watched it happen at normal human speed, you wouldn't have noticed anything at all. But compress 50 million years into a time lapse, and you'd see India sliding north like a ship through the ocean. The seafloor between India and Asia gradually disappearing into a subduction zone, the gap closing, and then the moment of contact. The edges of both continents would begin to crumple and fold, rock layers bending like putty, rising upward as the force of collision had nowhere else to go. Mountains would grow from hills to peaks, rising kilometer by kilometer into the sky. Even today, the Himalayas are still rising, still growing. Though we'll never notice it in our lifetimes. Mount Everest gains about 4 millimeters of height each year. At that rate, it will take 250 years to gain a single meter. By then, erosion will have worn away at least that much from the peak. Mountains grow, but they also wear down, weathered by wind, rain, ice, and time. The competition between uplift and erosion determines a mountain's height, and it's a slow, gentle competition with no winners, only this beautiful equilibrium. Think about the patience of a mountain. It takes millions of years to rise, and it might take millions more to wear away. But during those millions of years, it just stands there, existing, being a mountain. Clouds drift around its peak. Snow falls and melts and falls again. Trees grow on its slopes, their roots slowly, almost imperceptibly, working into cracks in the rock, helping to break it down, grain by grain. Animals live their lives in alpine meadows. Rivers begin as tiny springs and grow as they descend. All of this happens while the mountain slowly, peacefully continues its existence. Now, let's explore a different kind of plate boundary, where plates slide past each other horizontally. These are called transform boundaries, and the most famous example is the San Andreas Fault in California. Here, the Pacific Plate and the North American Plate grind past each other. The Pacific Plate moving northwest relative to North America. Los Angeles sits on the Pacific Plate, and San Francisco sits on the North American Plate, and over millions of years, they're slowly approaching each other. Don't worry though. At current rates, it will take about 15 million years for them to be side by side. That's longer than humans have existed as a species. It's hard to even comprehend a timescale that vast. 15 million years ago, our ancestors were still living in trees. Still small and furry, nowhere near the humans we'd become. 15 million years from now, who knows what species will inherit the Earth? But the plates will still be moving, patient and steady as ever. Most of the time, these plates slide smoothly past each other. The boundary between them isn't a single line, but a zone of many faults, a web of cracks where the rock can shift. In some places, the plates are stuck, friction holding them in place while stress builds up. Eventually, that stress releases in an earthquake, the plates suddenly jumping forward by a few centimeters or meters, catching up on all the motion that was prevented by friction. Then they stick again, and the process repeats. It's a pattern, a rhythm, though not a regular one we can easily predict. Between earthquakes, the fault zones are peaceful places. Grass grows in the rift valleys. Streams cut through the landscape. People build homes and live their lives, because most of the time, most of every year and decade and century, the ground is solid and still. The motion is there, always there, but it's patient. It waits, and most of the time, it expresses itself so gradually that we never notice at all. Let's travel now to East Africa, to the East African Rift Valley, one of the most fascinating places on Earth. Here, a continent is slowly splitting apart. Africa is breaking into two pieces. The Somali plate separating from the Nubian plate. This rifting is still in its early stages, geologically speaking. The Rift Valley is marked by dramatic escarpments, long cliffs where the land has dropped down along faults. Lakes fill the lowest parts of the valley, long and narrow, like tears in the fabric of the continent, millions of years from now. If the rifting continues, the Red Sea will extend southward, and a new ocean will separate East Africa from the rest of the continent. Somalia, Ethiopia, and parts of Kenya and Tanzania will become their own island, drifting away. But again, this will take tens of millions of years, time spans so long that they're almost meaningless to us. For now, the Rift Valley is just a beautiful, dramatic landscape, full of wildlife and human history. In fact, the Rift Valley has been incredibly important to human evolution. The landscape changes caused by rifting, the creation of diverse environments from forests to grasslands, may have driven the evolution of our ancestors. Fossils of early humans and their relatives have been found throughout the Rift Valley, preserved in layers of volcanic ash and sediment. The ground that was splitting apart created the conditions that shaped us. There's a lovely poetry in that, don't you think? The restless earth, creating the stage upon which life diversifies and adapts. Volcanic activity is common in rift valleys because, as the plates pull apart, the mantle beneath rises to fill the gap. This rising mantle can partially melt, creating magma that erupts at the surface. The Rift Valley has many volcanoes, including some of Africa's highest peaks. Mount Kilimanjaro, though technically just outside the main Rift Valley, is a volcanic mountain formed by related processes. It rises nearly 6 kilometers above sea level, its peak eternally covered in glaciers. Though sadly, those glaciers are shrinking due to climate change. The thing about rift valleys is that they remind us that continents aren't permanent. We think of them as fixed, as eternal, but they're just temporary configurations of rock floating on a dynamic planet. Once, all the continents were joined together in a supercontinent called Pangaea. About 200 million years ago, Pangaea began to break apart. First, it split into two large pieces, Laurasia in the north and Gondwana in the south. Then, these pieces continue to fragment, slowly drifting to their current positions. If you look at a map, you can still see evidence of this ancient connection. The east coast of South America and the west coast of Africa fit together like puzzle pieces. They were once joined, part of Gondwana. When they split apart, the Atlantic Ocean was born, starting as a narrow rift and gradually widening as the seafloor spread. The matching coastlines are just the most obvious evidence. The rock types match, too, and fossils of the same ancient species are found on both continents. Species that couldn't have crossed an ocean but could have lived in a unified landscape. Pangaea wasn't the first supercontinent, and it won't be the last. Before Pangaea, there was Pannotia, and before that, Rodinia. These supercontinents form and break apart in cycles lasting hundreds of millions of years. It's called the supercontinent cycle, and it's driven by the same forces that move the plates, heat from Earth's interior creating convection currents in the mantle. When continents come together, they insulate the mantle beneath them, causing heat to build up. Eventually, that heat creates a plume that rises, creating a rift, and the supercontinent begins to break apart. The continents drift, oceans open and close, and eventually, hundreds of millions of years later, the continents collide again, forming a new supercontinent in a different configuration. Imagine watching this process on a time-lapse, spanning 1 billion years. You'd see continents sliding across the globe like slow dancers, meeting and partying. Oceans appearing and vanishing, mountains rising and eroding away. The familiar shapes of our modern continents would be unrecognizable, just collections of rock following the currents below, painting ever-changing patterns on Earth's surface. And through it all, life would persist, adapting to every new configuration, filling every available niche, thriving in ways that we, in our brief moment of existence, can barely imagine. One of the most relaxing aspects of plate tectonics is its inevitability. These processes don't require maintenance or management. They don't depend on human action or inaction. They simply happen, driven by heat that's been flowing from Earth's interior for billions of years and will continue for billions more. Our planet is a heat engine, slowly cooling from its formation, and plate tectonics is one way that heat escapes. It's automatic, natural, and unstoppable in the most peaceful sense of that word. The movement of plates shapes our world in gentle ways, too, not just through dramatic mountains and volcanoes. The slow circulation of rock through the mantle helps regulate Earth's climate over geological time. Carbon dioxide from the atmosphere dissolves in rainwater, forming a weak acid that slowly weathers rock. That weathered rock washes into the ocean, where marine organisms use it to build shells. When those organisms die, their shells sink to the seafloor, locking carbon away in limestone. Eventually, that limestone might get subducted, and the carbon dioxide is released again through volcanic eruptions, returning to the atmosphere. It's a cycle that takes millions of years, but it keeps Earth's climate relatively stable on long time scales. Without plate tectonics, Earth might be very different. Venus, our sister planet, is about the same size as Earth, but has no plate tectonics. Its crust is a single solid lid. Heat can't escape efficiently, so it builds up until the entire surface melts and resurfaces all at once. Venus has a thick atmosphere of carbon dioxide and is hot enough to melt lead. Earth's plate tectonics, by constantly recycling the crust and regulating carbon dioxide, helps keep our planet habitable. The slow dance of the plates is part of what makes life possible. Let's continue our peaceful journey through the slow movements of our planet. We've explored how plates drift and collide, and now we'll discover more of the gentle wonders that happen when rock moves at the speed of growing fingernails. Think about the ocean floor for a moment. That vast landscape beneath the waves that most of us will never see. It's not flat and featureless as you might imagine. The seafloor has mountains taller than any on land, valleys deeper than the Grand Canyon, and plains that stretch for thousands of kilometers. All of this topography was created by the patient work of plate tectonics, built up grain or carved out as plates shifted and bent. The Mid-Ocean ridges form the longest mountain chain on Earth, stretching over 60,000 kilometers around the globe, like the seam on a baseball. These underwater mountains aren't sharp and jagged like the Rockies or the Alps. They're gentle slopes rising gradually from the abyssal plains. Hot rock wells up from below, creating new seafloor. And as it cools and moves away from the ridge, it contracts slightly, sinking a bit lower. This creates the slope. This soft descent from the ridge crest down to the deep ocean floor. Along these ridges, in the deep darkness where no sunlight penetrates, something wonderful happens. Hot water, heated by the magma below, rises through cracks in the newly formed rock. This water is full of minerals dissolved from the hot rock, and when it meets the cold ocean water, those minerals precipitate out, forming chimney-like structures called hydrothermal vents. Some of these vents release water that's hot enough to melt lead. But it doesn't boil because the pressure at these depths is so immense. Around these vents, entire ecosystems thrive in the darkness. Bacteria use the chemicals in the vent water as an energy source, a process called chemosynthesis, completely independent of sunlight. These bacteria form the base of a food chain that includes giant tube worms, white crabs, and strange fish. It's life thriving in one of Earth's most extreme environments, all made possible by the heat flowing from the planet's interior. The same heat that drives plate tectonics. There's something oddly comforting about this, knowing that life finds a way even in the deep darkness, sustained by the warmth of the earth itself. These hydrothermal vents might have been where life on Earth began, billions of years ago. The chemistry at these vents, the mixing of hot mineral-rich water with cold seawater, creates conditions that can form complex organic molecules. Some scientists think the first living cells might have emerged from this chemical mixing, protected and nourished by the steady heat from below. If that's true, then plate tectonics didn't just shape the surface of our planet. It created the very stage where life could begin. We are, in a very real sense, children of the moving earth. Let's drift upward now, back to the surface, and think about islands. Oceanic islands, the ones far from continents, are almost all volcanic in origin, created by magma rising from the mantle. Some are formed at spreading ridges, like Iceland, but others form in the middle of plates over what we call hotspots. A hotspot is a place where a plume of especially hot rock rises from deep in the mantle, perhaps from near the boundary between the mantle and the core. Nearly 3,000 kilometers below the surface, Hawaii is the most famous example of a hotspot island chain. The Hawaiian Islands are all volcanoes, built up from the seafloor by countless eruptions over millions of years. But here's the interesting part. The islands aren't all the same age. The big island of Hawaii in the southeast is the youngest, with volcanoes that are still active today. As you travel northwest through the chain, the islands get progressively older. Kauai, the northwesternmost of the main islands, is over 5 million years old and has no active volcanoes. This happens because the hotspot stays relatively fixed while the Pacific plate moves over it. Imagine holding a blowtorch under a slowly moving sheet of metal. The torch stays in one place, but the metal moves, so the torch burns a line of holes across it. That's essentially what's happening with Hawaii. The hotspot creates a volcano, but the plate carries that volcano away to the northwest. Eventually, the volcano is so far from the hotspot that it stops erupting, and a new volcano forms over the hotspot. Over millions of years, this creates a chain of islands, each one a chapter in a story written in volcanic rock. If you extend the Hawaiian chain even further northwest, beyond Kauai, you find older and older volcanic islands, most of them now just small atolls or seamounts, mountains that have eroded below sea level. The oldest parts of the Hawaiian Emperor seamount chain are over 80 million years old, stretching almost to the Aleutian Islands. That's 80 million years of continuous volcanic activity. The hotspot patiently creating island after island as the plate drifted over it. And it's still going. Beneath the ocean, southeast of the Big Island, a new volcano called Loihi is already growing. in a few 100,000 years, it might break the surface and become the next Hawaiian island. There are hotspots all over the world. Iceland sits on one, which is why it's so volcanically active, despite being on a spreading ridge. Yellowstone National Park in the United States sits above a hotspot, though unlike Hawaii, this one is beneath a continent. The geysers, hot springs, and colorful bacterial mats at Yellowstone are all surface expressions of that deep heat. Every time Old Faithful erupts, shooting hot water high into the air, it's a reminder that we live on a dynamic planet. That heat and motion continue in the depths, even when the surface seems solid and still. The movement of plates also creates something called terrains, which is a lovely word for a fascinating concept. A terrain is a piece of crust that formed somewhere else and then got attached to a continent through plate motion. Imagine you're walking along a beach and various things wash up at your feet. Driftwood, shells, bits of coral. Over time, these objects pile up along the shore, each one from a different place, brought together by the ocean's currents. That's similar to how terrains work, except the objects are pieces of ocean floor, volcanic islands, or even fragments of other continents. And they're brought together by the motion of tectonic plates. The western coast of North America is made up of many terrains, pieces that originated elsewhere and were gradually added to the continent over hundreds of millions of years. Some of these pieces traveled thousands of kilometers before colliding with North America. They brought their own rocks, their own fossils, their own geological histories. Scientists can identify terrains because their rocks don't match the surrounding continental rocks. They're foreigners, immigrants in the geological sense, now permanently part of North America, but still distinct, still preserving their own stories. There's something poetic about this. Continents aren't pure or homogeneous. They're collections of pieces assembled over time, each piece with its own origin story. The ground beneath your feet might have formed on the other side of an ocean that no longer exists, on an island that's now buried deep in a mountain range, or in some other configuration of the Earth's surface that existed before the dinosaurs, before complex life, before anything we would recognize as familiar. Let's think about the deep Earth now. The parts we can't see, but that drive everything we've been discussing. The mantle, that thick layer of hot rock between the crust and the core, isn't just sitting there. It's moving, convecting, like water boiling in a pot, but infinitely slower. Hot rock rises from the deep mantle, spreads out beneath the crust, cools as it releases heat to the surface, and then sinks back down. This takes millions of years for a complete cycle, but it's happening constantly, all over the planet. The core is even more fascinating. Earth's core is made mostly of iron, divided into a solid inner core and a liquid outer core. The inner core is about the size of the moon, a ball of solid iron-nickel alloy at a temperature of about 5,000 degrees Celsius, as hot as the surface of the sun. It's kept solid by immense pressure. The weight of the entire planet, the outer core, is liquid iron, and currents in this liquid iron generate Earth's magnetic field. Asterisk. That magnetic field is important for life on Earth. It extends far out into space, creating a protective bubble called the magnetosphere that deflects harmful solar radiation and particles streaming from the sun. Without this magnetic field, the solar wind would gradually strip away Earth's atmosphere, the way it did on Mars billions of years ago. The motion in the liquid core, driven by the heat flowing from the inner core, maintains this protective shield. It's one more way that Earth's internal heat, the same heat that drives plate tectonics, makes our planet habitable. The magnetic field isn't constant. It varies in strength, and occasionally it reverses, with the north and south magnetic poles swapping positions. This has happened hundreds of times over Earth's history. We know this because when volcanic rock cools, magnetic minerals in the rock align with Earth's magnetic field at that time, preserving a record of the field's direction. By studying rocks of different ages, scientists have mapped out the history of magnetic reversals going back hundreds of millions of years. These reversals don't happen suddenly. They take thousands of years to complete, during which the magnetic field becomes complex and chaotic, with multiple poles appearing in strange locations. Then it settles into the reversed configuration. The last reversal was about 780,000 years ago, which means we're probably due for another one eventually, but there's no way to predict when. It could be 1,000 years from now, or 100,000, and when it happens, it won't be catastrophic. The field won't disappear. It will just gradually shift and reconfigure. Life has survived hundreds of these reversals without any mass extinctions or disasters. Let's return to the surface and think about the shapes of continents. They're not random. The patterns we see, the locations of mountain ranges and lowlands, the positions of continents relative to each other. All of these are determined by plate tectonics. The ring of fire, that horseshoe of volcanoes and earthquake zones around the Pacific Ocean, outlines the Pacific Plate and its collision with surrounding plates. The great mountain ranges, from the Andes to the Himalayas to the Rockies, all mark places where plates have collided or are still colliding. Even the Atlantic Ocean tells a story. It's young, in geological terms, only about 200 million years old. Before it opened, before Pangaea split apart. The Appalachian Mountains of North America were connected to mountains in Scotland and Norway. They were part of one great mountain range, formed when ancient continents collided long before Pangaea even existed. When Pangaea broke apart, it didn't break along the old collision zone. Instead, it split along a new line, separating the mountains. Now, half of that ancient mountain range is in North America, and half is in Europe, separated by an ocean, but still matching in age and rock type. The Appalachians are old now, worn down by hundreds of millions of years of erosion. They were once as tall as the Himalayas, but time has been patient with them. Rivers have carved valleys, glaciers have scraped and scoured, wind and rain have weathered the peaks. What remains are gentle, rounded mountains covered in forests, beautiful but subdued. In another 100 million years, they might be worn down to flat plains. But then again, maybe the plates will collide again, and new mountains will rise from the same rocks. The cycle continues, and nothing is truly permanent except change itself in the ocean basins. The abyssal plains are some of the flattest places on Earth. These vast underwater plains are covered by sediment, tiny particles that have drifted down from the surface over millions of years. Dead plankton, dust blown from continents, dissolved minerals that precipitate from seawater. All of it settles gently to the bottom, accumulating at a rate of perhaps a centimeter per 1,000 years. It takes patience to build these plains, layer upon microscopic layer, but time is something Earth has in abundance. Beneath the sediment, the basalt of the ocean floor preserves a record of its journey from the spreading ridge. As the rock formed and cooled, magnetic minerals in it aligned with Earth's magnetic field. If you could map the magnetic patterns in the ocean floor, you'd see stripes, alternating bands of normal and reversed polarity, perfectly symmetrical on either side of the ridge. These stripes are a beautiful confirmation of seafloor spreading, showing that new ocean floor forms at the ridge and moves away in both directions, recording each magnetic reversal as it goes. Scientists discovered these magnetic stripes in the 1960s, and they were crucial evidence for plate tectonics. Before then, many geologists were skeptical that continents could move. The magnetic stripes proved it beyond doubt. The ocean floor was a recording tape, preserving a history that could be read by anyone who knew how to interpret it. It was one of those moments in science where everything suddenly made sense, where observations that seemed unrelated suddenly fit together into a unified picture. The ground beneath our feet wasn't static. It was part of a dynamic system, constantly moving and renewing itself. Let's think about earthquakes now, but in a gentle way. Yes, earthquakes can be destructive and frightening when they happen in populated areas. But most earthquakes are small, and most happen in places where nobody feels them. Thousands of tiny earthquakes happen every day as plates adjust their positions, releasing small amounts of stress. These microquakes are far too small for humans to feel, but sensitive instruments detect them constantly. A quiet reminder that the Earth is always in motion, even the larger earthquakes, while dramatic, are just the Earth finding a comfortable position. Imagine sitting in a chair for a long time. Eventually, you shift your weight, adjusting slightly to be more comfortable. That's essentially what the Earth is doing. The plates are trying to move, but friction holds them in place. Stress builds up until it overcomes the friction, and then the plates suddenly shift to a new position. It's not malicious or destructive by intent. It's just physics, just the mechanics of a dynamic planet. After a major earthquake, the affected area experiences aftershocks, smaller quakes, as the crust adjusts to its new configuration. These aftershocks can continue for months or even years, gradually decreasing in frequency and magnitude. It's like the Earth is settling, finding equilibrium again. And between earthquakes, life continues. Buildings stand, rivers flow, trees grow. Most of the time, even on active faults, the ground is peaceful and solid. The oldest rocks on Earth's surface are about 4 billion years old, found in ancient continental core called cratons. These regions have been stable for billions of years, far from active plate boundaries, just sitting quietly while the rest of the world rearranges itself around them. The Canadian Shield, the Australian outback, parts of Africa and Siberia. These are the ancient hearts of continents, the stable cores that have witnessed almost the entire history of plate tectonics. These ancient rocks have been metamorphosed, changed by heat and pressure, sometimes multiple times over their long existence. The minerals have been rearranged, the rock layers folded and twisted, but the rocks endure. They're survivors, witnesses to events we can barely imagine. 4 billion years ago, Earth was a very different place. The atmosphere had little oxygen, the sun was dimmer, the moon was closer and appeared larger in the sky. But even then, plate tectonics might have been operating, though perhaps differently than today. Heat had to escape from Earth's interior, and movement was the way to do it. Asterisk, as Earth has cooled over billions of years, plate tectonics has likely slowed down. Early in Earth's history, the mantle was hotter, and plates might have moved faster. There might have been more plates, smaller ones, moving and colliding more frequently. But the basic process was probably the same. Heat rising, rock moving, continents drifting, oceans opening and closing. And this will continue into the future, as long as Earth's interior remains hot enough to drive convection in the mantle. How long will that be? Billions of years, certainly. Earth's internal heat comes from two sources. The leftover heat from the planet's formation, when countless collisions of space debris released enormous energy, and the radioactive decay of elements like uranium, thorium, and potassium. These radioactive elements are scattered throughout Earth's mantle and crust, and as they decay, they release heat. This process will continue for billions of years, slowly declining but never quite stopping, eventually, far in the future. Earth's interior will cool to the point where plate tectonics stops. The crust will become a solid lid, like Venus's. Heat will have to escape through volcanoes rather than through the organized circulation of plates. The surface will become more static, less dynamic. Mountain building will slow and eventually stop. Erosion will continue, wearing down the mountains that exist. And eventually, Earth's surface might become relatively flat, covered by a global ocean with perhaps a few low islands. But that's billions of years away, so far in the future that it's almost meaningless to us for now. And for countless generations to come, we live on a dynamic planet. The ground beneath us moves, mountains rise, oceans open and close. And all of this happens so slowly, so patiently, that we can simply appreciate the beauty of it without worry. We're passengers on these great plates of rock, riding currents we can't feel, on a journey that's been ongoing for billions of years and will continue long after humanity is gone. Asterisk, there's deep comfort in that perspective. Our individual worries, our daily stresses, they're so brief compared to the timescales of geology. A human lifetime is barely a moment in the life of a mountain. In the time it takes a person to be born, grow old, and pass away, a tectonic plate might move a few meters. That's all. Just a few meters in 70 or 80 years of planetary motion. And yet, over millions of years, those few meters per lifetime add up to thousands of kilometers, to the opening of oceans and the raising of mountains. The slowness is the point. The patience is what makes it work. If plates moved quickly, the energy released would be catastrophic. But they move slowly, and that slowness spreads the energy out over vast periods of time, making it gentle, manageable, part of the background rather than a crisis. The Earth isn't in a hurry. It has time, all the time in the world, literally. And so do we in our own way. We have this moment, this brief, beautiful moment, to exist on a living planet, to witness the outcomes of billions of years of patient motion. Let's continue our peaceful exploration of the moving Earth, diving deeper into the gentle rhythms that shape our world. We'll discover how the patient dance of tectonic plates creates landscapes of stunning beauty, and how even the most dramatic geological events unfold with a slowness that's deeply calming when you understand the timescales involved. Consider the formation of a single crystal of quartz in a cooling body of magma deep underground. As the magma cools, silicon and oxygen atoms drift through the liquid rock, occasionally bumping into each other in just the right configuration to start forming a crystal lattice. More atoms attach one by one, building the crystal layer by atomic layer. This might take thousands of years for a crystal the size of your fingernail. There's no rush, no deadline. The atoms have all the time they need to find their proper positions, creating a structure of perfect geometric harmony. These crystals grow in magma chambers beneath volcanoes, massive underground pools of molten rock that can be several kilometers across. The magma doesn't sit still. It convects, slowly circulating as hotter magma rises from below and cooler magma near the walls sinks. This circulation can take years or decades for a single complete cycle. While it circulates, the magma gradually cools and different minerals crystallize out at different temperatures. The first minerals to form are usually olivine and pyroxene, dark minerals rich in iron and magnesium. As these crystals form, they sink to the bottom of the chamber because they are denser than the remaining liquid. The remaining magma becomes enriched in silica, aluminum, and other lighter elements. As cooling continues, more minerals crystallize, each type forming at its characteristic temperature. Feldspar crystals grow, then quartz, then perhaps mica. Each mineral takes its turn, patiently waiting for conditions to be just right. Eventually, if the magma cools slowly enough, deep underground, where it's insulated by surrounding rock, it solidifies completely into granite. A rock composed of interlocking crystals large enough to see with the naked eye. Granite forms the cores of most mountain ranges, the deep roots that support the peaks above. When you see granite exposed at the surface, you're looking at rock that formed kilometers underground, then was slowly uplifted as mountains rose, and gradually revealed as erosion stripped away the overlying rock. This process takes tens of millions. The granite you see today in places like Yosemite or the Scottish Highlands formed deep underground long ago, when dinosaurs still walked the earth, or even earlier, and has been patiently waiting to see sunlight. Let's think about erosion now, the other half of the mountain building story. Erosion is just as patient as uplift and just as relentless. Every raindrop that falls on a mountain dissolves a tiny amount of mineral from the rock surface. That mineral-rich water flows downhill, joining streams, then rivers, eventually reaching the ocean. Each raindrop removes such a tiny amount that you'd never notice But multiply that by billions of raindrops, by millions of years, and entire mountains can be worn down to sea level. Rivers are nature's sanders and polishers. They carry sediment, sand, and silt and clay, and this sediment acts like sandpaper, grinding away at the riverbed. Over thousands of years, a river can cut a deep canyon through solid rock. The Grand Canyon was carved by the Colorado River over the past 5 to 6 million years. That sounds like a long time, and it is by human standards, but it's actually quite recent in geological terms. The rocks at the bottom of the canyon are nearly 2 billion years old, but the canyon itself is young, a fresh cut through ancient layers. What's remarkable is that you can read Earth's history in those canyon walls. Each layer of rock represents a different time period, a different environment. There are layers of sandstone that were once beaches or deserts, layers of limestone that were once shallow tropical seas, layers of shale that were once muddy river deltas. The oldest rocks at the bottom are metamorphic, twisted and altered by heat and pressure during some ancient mountain building event. Looking at these layers is like looking at pages in a book, each one telling a story about what Earth was like when that layer formed. And all of these layers were horizontal when they formed. Because sediment settles in horizontal layers. But if you look at many rock formations, especially in mountain ranges, you'll see layers that are tilted, folded, even turned completely vertical or upside down. This tilting happened as tectonic forces compressed and deformed the rocks, usually during mountain building. The rocks were bent like putty, even though they seem hard and brittle to us. Over millions of years, with enough heat and pressure, even solid rock can flow and fold. There's a beautiful mountain in Canada called Mount Rundle in the Canadian Rockies. If you look at it, you can see the rock layers are tilted at a dramatic angle, like a stack of books leaning over. These layers were once flat-lying seafloor sediments. Then, when the North American plate collided with terrains from the Pacific, the compression folded and tilted these layers, lifting them thousands of meters into the air. Now they're mountain peaks, decorated with snow and ice, carved by glaciers into dramatic shapes. The layers tell the story of their journey from seafloor to mountaintop, a journey spanning hundreds of millions of years. Glaciers are another patient sculptor of landscapes during ice ages, which occur every 100,000 years or so in a regular cycle driven by changes in Earth's orbit. Vast ice sheets grow and cover large portions of the continents. These ice sheets can be several kilometers thick, and their weight is immense. The ice flows like a very slow river, creeping downhill at rates of perhaps a few meters per year. As it moves, it picks up rocks and boulders, and these embedded rocks scrape and gouge the bedrock beneath, carving valleys and polishing surfaces when the ice age ends and the glaciers melt. They leave behind a transformed landscape. Valleys that were V-shaped from river erosion are now U-shaped, widened and deepened by the ice. The bedrock is polished smooth, in some places scratched with parallel grooves in others, showing the direction the ice moved. Boulders that were carried by the ice and deposited far from their source, called erratics, sit incongruously on the landscape. Sometimes different types of rock than anything nearby, silent witnesses to the power and patience of moving ice, the great lakes of North America were carved by glaciers during the last ice age. These enormous lakes, more like inland seas, occupy basins that were scoured out by massive ice sheets. When the ice melted about 10,000 years ago, the basins filled with meltwater, creating the lakes we know today. They're still adjusting to the removal of that weight. The land beneath them, freed from the burden of kilometers-thick ice, is slowly rising, rebounding at a rate of a few millimeters per year. This process, called isostatic rebound, will continue for thousands more years until the land reaches a new equilibrium. Scandinavia is doing the same thing. During the last ice age, an ice sheet covered Norway, Sweden, and Finland. That ice is gone now, but the land is still rising, still recovering from being pressed down. Harbors that were at sea level in Viking times are now above the water. Ancient beaches are now high and dry, stranded inland. The land rises slowly, patiently making up for the time it spent compressed beneath ice. Asterisk. Let's travel to a different type of landscape. The great rift valleys we mentioned earlier. The East African Rift is perhaps the most dramatic, but there are others. The Rio Grande Rift in New Mexico, the Rhine Graben in Europe, the Baikal Rift in Siberia. All of these are places where the crust is being stretched and thinned, where continents are starting to break apart. The process is slow, and most of these rifts will probably never fully separate their continents. But they give us a window into how rifting works in a rift valley. The land drops down along parallel faults, creating a depression between uplifted shoulders. It's like the land is sinking in the middle, while the edges stay high. This happens because as the crust stretches, it thins, and thinner crust sits lower because it's less buoyant. The faults don't move smoothly. They stick, stress builds up, and then they suddenly slip, causing an earthquake. Between earthquakes, the Rift Valley is a peaceful place, often home to lakes, rivers, and abundant wildlife. Lake Baikal in Siberia is the deepest lake in the world, over 1,600 meters deep, and it sits in a rift valley. The lake is also incredibly old, about 25 million years, making it the oldest lake in the world. Most lakes are temporary features in geological terms, filling in with sediment or draining within a few tens of thousands of years. But Baikal persists because the rift is still active, still deepening, creating space for the lake faster than sediment can fill it in. The lake is also home to unique species found nowhere else. Animals that evolved in isolation over millions of years, adapting to life in this ancient rift lake. The water in Lake Baikal is astonishingly clear. You can see down more than 40 meters in some places. This clarity comes from tiny crustaceans that filter the water, removing particles and keeping it clean. These crustaceans are endemic to Baikal, found nowhere else on Earth. They're part of an ecosystem that's both ancient and isolated. A reminder that even geological features like rift valleys create unique environments where life can flourish in its own distinctive ways. Let's think about the rocks beneath our feet in a different way now. Not as static objects, but as participants in a slow cycle. The rock cycle, it's called, and it's driven by the same heat and motion that powers plate tectonics. Igneous rocks form from cooling magma or lava. These rocks can be weathered and eroded, broken down into sediments that are transported by wind or water and eventually deposited in layers. As more sediment piles up, the weight compresses the lower layers, and minerals precipitate from water percolating through the sediment, cementing the grains together. This creates sedimentary rock. If sedimentary rock gets buried deep enough, perhaps by continued sedimentation or by being caught in a zone of plate collision, it experiences increasing heat and pressure. The minerals in the rock start to change, rearranging into new forms that are stable at higher temperatures and pressures. The rock is metamorphosing, changing from one type to another. Shale becomes slate, then with more heat and pressure, schist, and finally, gneiss. Limestone becomes marble. Sandstone becomes quartzite. The rock never melts. It remains solid throughout, but its minerals transform, creating new textures and structures. If the rock gets buried even deeper, or if magma intrudes nearby, it might eventually melt, becoming magma itself. That magma might rise and cool to form new igneous rock, completing the cycle. Or the metamorphic rock might be uplifted and exposed at the surface, where erosion will break it down into sediment, starting another turn of the cycle. There's no set path, no required sequence. A rock might go from igneous to sedimentary to metamorphic and back to igneous. Or it might go from igneous to sedimentary and stay there for hundreds of millions of years before being metamorphosed. The cycle has no beginning and no end, just continuous transformation. This cycle has been operating since Earth had a solid crust for over 4 billion years. The atoms in rocks have been recycled countless times, formed into igneous rock, weathered away, deposited as sediment, compressed, metamorphosed, melted, and crystallized again. The calcium atom in your bones might have once been part of a limestone deposited in an ancient sea, and before that, part of the shell of some marine creature, and before that, dissolved in seawater, and before that, weathered from an igneous rock in some long-vanished mountain range. Everything connects, everything cycles, and nothing is truly permanent. Even the most stable-seeming landscapes are temporary. The Sahara Desert, for instance, hasn't always been a desert. A few thousand years ago, it was much greener, with lakes and rivers and grasslands. Rock art from that period shows people herding cattle and hunting hippos, animals that need water and vegetation. The change to desert conditions happened as Earth's climate shifted, as changes in Earth's orbit altered the patterns of rainfall. And in the future, the Sahara might become green again, in another cycle of climate change driven by those same orbital variations. These climate cycles, called Milankovitch cycles, operate on timescales of tens of thousands to hundreds of thousands of years. They're caused by subtle changes in Earth's orbit around the Sun and the tilt of Earth's axis. These changes affect how much sunlight reaches different parts of Earth at different times of year, which influences climate. The ice ages of the past 2 million years have followed these cycles, with glaciers advancing and retreating in rhythm with the orbital changes. But plate tectonics influences climate too, on even longer timescales. The position of continents affects ocean currents, which redistribute heat around the planet. When continents are clustered near the poles, as Antarctica is now, ice can accumulate because the land provides a stable platform for ice sheets. When continents are near the equator, as most were during the Cretaceous period, the climate is warmer overall because there's no land at the poles for ice to form on. The opening and closing of ocean gateways also matters. When the Isthmus of Panama formed about 3 million years ago, connecting North and South America, it closed off a tropical current between the Atlantic and Pacific. This changed circulation patterns in the Atlantic, possibly triggering the series of ice ages we've experienced since then. Mountains also affect climate. When the Himalayas rose, they created a barrier to atmospheric circulation, altering monsoon patterns across Asia. The uplift of mountains also increases erosion rates, and as rock is weathered, it consumes carbon dioxide from the atmosphere. This can cool the climate over millions of years. Some scientists think the rise of the Himalayas and the Tibetan Plateau over the past 50 million years has contributed to the overall cooling trend that Earth has experienced during that time. A cooling that eventually led to the ice ages. All of these processes interact in complex ways. Plate tectonics shapes the distribution of continents. The continents influence ocean currents and atmospheric circulation. Climate affects weathering rates and the distribution of ice. Ice sheets affect sea level and the climate. Everything is connected. Everything influences everything else. And it all operates on timescales so long that we can barely comprehend them. Yet these processes are also regular, predictable in their patterns, if not in their exact timing. There's a rhythm to Earth's behavior, a slow dance of rock and water and air and ice, all moving together, all influenced by the heat flowing from the planet's interior. When you understand these connections, when you see how everything fits together, there's a profound sense of peace that comes with it. The world isn't chaotic. It's complex, yes, but it follows patterns, operates according to physical laws that are consistent and understandable. The ground beneath your feet isn't random. It's the product of billions of years of processes that continue today. Processes we can study and understand and even predict to some extent. And you're part of this system too. The oxygen you breathe was produced by plants and algae through photosynthesis, using carbon dioxide from the atmosphere. That carbon dioxide came partly from volcanic eruptions, partly from the weathering of rock, partly from the respiration of living things. The water you drink has cycled through the oceans, the atmosphere, rivers, groundwater, and living things countless times. The minerals in your body were once part of rocks, weathered away and dissolved, taken up by plants, passed through food chains, and eventually incorporated into your bones and tissues. You're made of earth, quite literally. The calcium in your bones, the iron in your blood, the carbon in your cells. All of these elements were forged in stars that exploded long before the sun and earth formed. They were part of the cloud of gas and dust that collapsed to form the solar system. They've been part of Earth for 4.5 billion years, cycling through rocks and oceans and living things, temporary inhabitants of countless different molecules and structures. And after you, they'll continue cycling, becoming part of new rocks, new oceans, new life. Nothing is created or destroyed, just transformed, endlessly recycled in the great cycles of Earth and cosmos. There's something deeply comforting about being part of something so vast, so ancient, and so ongoing. Your individual existence is brief, but you're connected to a story that spans billions of years and will continue for billions more. The atoms in your body have already existed for eternity, from a human perspective, and they'll continue existing long after you're gone. You're a temporary arrangement of these atoms, a pattern that exists for a few decades and then dissolves. But the atoms themselves are nearly immortal. And the processes that move those atoms around, that build mountains and open oceans and cycle rock through the planet's interior, these processes are driven by heat, by the energy that was trapped in Earth when it formed, and by the energy released by radioactive decay. This heat flows steadily outward, has been flowing for billions of years, will continue flowing for billions more. It's automatic, unstoppable, and utterly reliable. The Earth will keep being geologically active as long as that heat remains. And there's enough heat left for billions of years yet. So rest easy, knowing that the ground beneath you is part of a vast, slow, patient system that's been operating since before life existed and will continue operating long after the last living thing is gone. The plate will keep moving, mountains will keep rising and eroding away. Oceans will keep opening and closing, and all of it will happen so slowly, so gently, that there's nothing to worry about, nothing to fear. It's just the Earth being Earth, doing what it's done for eons, following the laws of physics with perfect consistency, creating beauty and complexity through simple processes operating over immense spans of time. As we reach the final part of our peaceful journey through the moving Earth, let's explore some of the most serene and beautiful consequences of plate tectonics and reflect on what these slow, patient processes mean for us and for the planet we call home. Think about hot springs for a moment. Those pools of naturally heated water that bubble up from the ground in volcanic areas. The water in a hot spring might have fallen as rain on a mountain years or even decades ago. It percolated down through cracks in a rock, descending deeper and deeper into the Earth's crust. As it descended, the water warmed, heated by the rocks around it, which are warm because of the magma chambers below. Eventually, the water became hot enough to dissolve minerals from the surrounding rock, picking up silica, calcium, sulfur, and other elements. The heated water becomes less dense than the cold water around it. So it begins to rise, following pathways through the fractured rock. It might take years to complete this journey, slowly ascending through kilometers of stone, gradually cooling a bit, but still carrying that deep earth warmth. Finally, it emerges at the surface as a hot spring, releasing its heat and minerals into a pool where, throughout human history, people have come to bathe and relax. The minerals precipitate out as the water cools, forming colorful deposits around the spring. Layers of travertine or silica in shades of white, yellow, orange, and red dot. The thermal pools at Yellowstone are famous for their brilliant colors. The deep blue of some pools comes from the water itself, so pure and deep that it scatters blue light. The yellows, oranges, and greens come from thermophilic bacteria and archaea, microscopic organisms that thrive in hot water. Different species prefer different temperatures, so they form colorful bands around the pools, creating natural rainbows of life in water that would be far too hot for most organisms. These bacteria are ancient descendants of some of Earth's earliest life forms, still thriving in environments similar to those where life might have first emerged. Japan has thousands of hot springs called onsen, and visiting them is a cherished tradition. People soak in the mineral-rich water, letting the warmth seep into tired muscles, breathing steam that carries the faint smell of sulfur. The practice of bathing in onsen is about more than cleanliness. It's about relaxation, about taking time to be still, to let the warmth of the earth itself soothe you. There's something profound about that, about being warmed by heat that originated deep underground. Heat that's been flowing from the planet's interior for billions of years. Iceland is another land of hot springs, sitting as it does on both a spreading ridge and a hot spot. The Icelanders have harnessed this geothermal energy, using it to heat homes and greenhouses, to generate electricity, to warm the water in swimming pools. Nearly 90% of homes in Iceland are heated with geothermal energy, a gift from the volcanic landscape, from the heat rising along the plate boundary. It's a reminder that plate tectonics isn't just about mountains and earthquakes. It's also a source of energy, a resource that humanity can use sustainably, drawing on heat that will keep flowing for millions of years. Geothermal energy is used around the world. Anywhere there's accessible heat beneath the surface. The Philippines, Indonesia, New Zealand, Italy, all of these countries harness geothermal power. The heat is always there, always flowing upward, and we've learned to tap into it, to use it without depleting it, because the source is so vast. It's one of the most sustainable energy sources available, powered not by sunlight or wind, but by the primordial heat of Earth's formation and the decay of radioactive elements. As long as Earth exists, this heat will be there. Let's think about beaches now, those peaceful places where land meets sea. The sand on a beach is the end product of weathering and erosion. Tiny fragments of rock that have been broken down and transported by rivers to the coast. Each grain of sand might have traveled hundreds of kilometers from some inland mountain, carried grain by grain downstream, tumbled and smoothed by the journey. The minerals in beach sand tell you about the rocks upstream. Quartz is common because it's hard and resistant to weathering. But you might also find feldspar, mica, tiny fragments of shells, even particles of volcanic glass on some beaches. The sand is black, made of basalt fragments from volcanic eruptions. Hawaii has black sand beaches, created when hot lava flows into the ocean and shatters into tiny particles. The fragments are sharp at first, but wave action gradually smooths them. In a few places, beaches are green, colored by olivine crystals eroded from volcanic rocks. The olivine is heavier than quartz, so green sand beaches are rare, found only in places with very specific geology and wave conditions. White sand beaches, like those in the Caribbean, are often made not of rock fragments, but of biological material. The sand is mostly calcium carbonate from coral reefs and shells that have been broken down by waves and by fish that graze on algae growing on coral. Parrotfish are particularly important. They bite off chunks of coral, digest the algae, and excrete the calcium carbonate as fine sand. A single parrotfish can produce hundreds of kilograms of sand per year. So that beautiful white sand beach is, in a very real sense, fish poop endlessly recycled by the ocean, spread along the shore by waves and currents. The waves themselves are powered by wind, which is powered by the sun heating the atmosphere unevenly. But the ocean basins that contain those waves, the continental shelves where beaches form, the coastlines where waves break, all of these are shaped by plate tectonics. The Atlantic coastline of North America is a passive margin, meaning it's not at a plate boundary. The continental shelf there is wide and gently sloping, creating excellent conditions for beaches. The Pacific coast is an active margin closer to a plate boundary, with a narrower continental shelf and more dramatic coastline. Both are beautiful, but in different ways, and both owe their character to plate tectonics, sea level changes over time, rising and falling as climate changes and ice sheets grow or melt. During the last ice age, sea level was more than 100 meters lower than today, because so much water was locked up in ice sheets. The coastlines were far out beyond where they are now. You could walk from England to France. Florida was twice as wide. Islands in Southeast Asia were connected to the mainland. Then the ice melted, sea level rose, and the ocean reclaimed those lands. Ancient human sites from that time are now underwater, submerged on the continental shelf. Asterisk in the future. If climate continues to warm and ice sheets melt, sea level will rise further. But even that change, dramatic as it might be for coastal communities, is just another variation in the ongoing story of Earth's surface. Sea level has been much higher in the past and much lower. During the Cretaceous period, sea level was so high that shallow seas covered much of what's now dry land. Chalk deposits, like the famous White Cliffs of Dover, formed from the shells of countless microscopic organisms living in those warm, shallow seas. The chalk is soft and easily eroded now, but it preserves a record of a time when Earth was warmer, when plate tectonics had arranged continents differently, when the world was strange and different, yet still beautiful. Let's think about islands again, but this time about coral atolls. Those rings of coral reef surrounding lagoons in tropical oceans. Charles Darwin proposed an explanation for how atolls form. And he was right, even though he never saw the evidence that would prove his theory. An atoll begins as a volcanic island rising from the seafloor. Corals grow in the warm, shallow water around the island, building a fringing reef. Over time, the island begins to sink. This happens because as a volcanic island ages, as the plate moves away from the hotspot or spreading ridge that created it, the rock cools and contracts, and the seafloor beneath it subsides, settling lower under the island's weight. As the island slowly sinks, the corals keep growing upward, staying near the surface where sunlight can reach them, because corals have a symbiotic relationship with photosynthetic algae. The reef grows upward at the same rate the island sinks, or close to it. Eventually, the volcanic island disappears completely beneath the surface. But the reef remains, now surrounding a lagoon where the island used to be. This transformation takes millions of years, the coral building steadily upward while the island slowly vanishes below. The result is an atoll, a ring of living reef enclosing a peaceful lagoon, often with small islands made of coral sand on the reef rim. Drilling through atolls has confirmed Darwin's theory. Beneath the coral, under hundreds of meters of reef limestone, volcanic rock is found, the base of the original island. The corals have been growing for millions of years, building layer upon layer, creating these delicate rings of life that dot tropical oceans. There's something wonderfully patient about corals. These tiny animals that secrete calcium carbonate skeletons, generation after generation, building structures that can be seen from space, all while the island they started on slowly sinks into the sea. The diversity of landscapes on Earth is a direct result of plate tectonics. Without it, without the motion and recycling and mountain building and volcanic activity, Earth would be a very different place. It might be a smooth ball covered entirely by ocean, with no continents, no mountains, just water and perhaps a few volcanic islands. All the interesting topography, all the variety of environments, from high mountains to deep ocean trenches to rift valleys to volcanic islands. All of it exists because plates move and interact. And this diversity creates opportunities for life. Different environments select for different adaptations. Life diversifies, spreading into every available niche, evolving in response to challenges and opportunities. The variety of life on Earth, the millions of species, are here because plate tectonics created a variety of environments for them to live in. Mountain ranges isolate populations, allowing them to evolve separately. Volcanic islands provide blank slates where new species can emerge. Rift valleys create unique aquatic environments. Subduction zones create deep ocean trenches where specialized creatures thrive in the darkness. Plate tectonics even influenced human evolution. The formation of the East African Rift Valley, with its varied topography and changing climate, may have created conditions that favored the evolution of our ancestors. The rift created forests, grasslands, lakes, and rivers in close proximity, a complex landscape that rewarded intelligence and adaptability. Our ancestors evolved in this dynamic environment, learning to use tools to hunt and gather in different habitats, to work together and communicate. In a sense, we are children of the rift, shaped by a landscape that was itself shaped by the slow splitting of a continent dot. Now, as we near the end of our journey, let's reflect on what all of this means. We live on a planet that's alive, not in the biological sense, but in the geological sense. Earth is dynamic, changing, never static. The ground beneath us moves, mountains rise and erode, oceans open and close. And all of this happens according to physical laws, driven by heat, governed by the properties of rock and the force of gravity. It's not random or chaotic. It's ordered, it's predictable in its patterns, even if not in every detail. This ongoing change means that Earth has a history, a story that can be read in its rocks and landscapes. Every mountain range is a chapter about collision and uplift. Every ocean basin tells of spreading and subduction. Every rock is a record of conditions at the time it formed. And because these processes continue, Earth also has a future. A story that's still being written, one that will continue long. Understanding this gives us perspective. The challenges we face as individuals, as societies, they're real and important on human timescales. But on geological timescales, they're brief moments. The Earth has experienced countless changes, countless challenges, and it endures. Life has survived ice ages, asteroid impacts, massive volcanic eruptions, and it continues, adapting, evolving, persisting. There's resilience in nature, a kind of patient endurance that comes from operating on these vast timescales. That doesn't mean our actions don't matter. We can change Earth's surface, alter its climate, affect its ecosystems. But it does mean that Earth will continue beyond us, that the processes we've discussed will keep operating, that new mountains will rise and new oceans will open, regardless of what we do. The planet will be fine in the long run. It's we who need to be concerned with creating conditions we can live in, with maintaining the kind of world that supports us and the life we depend on. There's comfort in understanding our place in this vast system. We're not separate from nature. We're part of it, participants in the great cycles of rock and water and air. The calcium in our bones came from ancient seas. The oxygen we breathe was produced by photosynthetic organisms using energy from the sun and carbon from volcanic eruptions. The ground we walk on is part of a plate that's slowly moving, carrying us on a journey we can't feel, but that continues nonetheless. We're embedded in these systems, connected to them in countless ways. And so, as you drift toward sleep, let yourself feel that connection. You're lying on a planet that's ancient beyond comprehension, yet still active, still changing. The rock beneath you is part of a cycle that's been operating for billions of years. The atoms in your body have been part of that cycle, have been rock and water and air and life countless times before. You're a temporary arrangement of ancient material, a brief pattern in the endless flux of matter and energy that is our living planet. The plates beneath you are moving right now, slowly, steadily, at the speed of growing fingernails. In some distant future, continents will be in different positions. New mountains will have risen where now there are plains. Old mountains will have been worn flat. Oceans will have opened and closed. But all of that will happen so slowly, so gently, that there's nothing to worry about tonight. Nothing to think about except the simple fact of being here, now. Part of this ancient and ongoing story. Let the slowness of geological time calm you. Let the patience of tectonic processes soothe you. Mountains don't rush to grow. Rivers don't hurry to carve canyons. Plates don't race across the globe. Everything happens in its own time, at its own pace, following natural rhythms that need no adjustment, no correction, no intervention. It just happens, has been happening, will keep happening. The earth breathing in stone, dreaming in continental drift, expressing itself through volcanism and orogene and the patient sculpture of wind and water. You're safe here, on this dynamic yet stable planet. The ground is solid beneath you, even though it's moving. The processes that shape Earth operate on timescales so long that you'll never perceive them directly. Doing their slow work, creating beauty through patience, generating complexity through simple rules applied over vast stretches of time. And you're part of it all, a conscious piece of Earth. made of Earth, thinking about Earth before returning to Earth. Your atoms joining again the great cycles that have no beginning and no end. So rest now. Let yourself be held by the planet, supported by rock that's been here for millions or billions of years and will be here long after you're gone. Let your breathing slow to match the pace of geological processes. Let your thoughts drift like continents crossing ancient oceans. Let yourself sink into the deep time that surrounds and supports us all. That perspective that makes everything seem less urgent, less frightening, less overwhelming. In the vast scope of Earth's history, this moment is infinitesimally brief. Yet it's also infinitely precious because it's yours. Your moment to experience existence on a living world. The plates will keep moving tonight while you sleep. Mountains will rise by nanometers. Rivers will carry away grains of sand. Magma will slowly convect in chambers beneath volcanoes. The core will generate its magnetic field. The mantle will flow in its slow currents. And all of this will happen without you needing to think about it, without you needing to do anything at all. The Earth takes care of itself, follows its own rhythms, and you can simply rest, knowing that these ancient processes continue, reliable and patient, the foundation upon which all life, including yours, exists. Sleep well, secure in the knowledge that you live on a planet that's been successfully operating for 4.5 billion years and knows exactly what it's doing. Dream of continents drifting, of mountains rising from seas, of rivers of stone flowing beneath the crust, of crystals growing in darkness, of volcanic islands blooming from ocean floors, of all the patient, beautiful processes that make Earth the remarkable place it is. And when you wake, the plates will have moved a tiny bit further. Your fingernails will have grown a fraction of a millimeter, and life will have continued its endless, creative dance on the surface of our moving, living, patient planet.